Okay, so let's start today with double integrals over rectangles, okay? So, let's say that we have a region R, which is going to equal all of the xy values, such that A is going to be less than or equal to x, which is going to be less than or equal to b, and C is going to be less than or equal to y, which is going to be less than or equal to d. Okay? So we want to integrate over this region, calculating the volume of a function. So we have a z as a function of x and y, and we want to calculate the volume under that. So the double integral upon that region of f of x, y, and we are going to integrate with respect to the area, okay, is going to equal the integral from a to b of the integral from c to d of f of x, y. Okay, now the c and the d are corresponding to the y value. So this inner integral is going to be an integral with respect to y. Now a and b are going to correspond to the x boundaries. So that's going to be the integral with respect to x. Okay. Now, over general regions, switching these things becomes an issue. You have to actually change the functions around. But since we're just talking about a rectangle at this point, we can switch these out. So, this is the same thing as writing the integral from c to d of the integral from a to b of f of x, y. Now this would be dx dy. So when we're talking about just rectangles, yeah, you can switch the order of it. It's not that big of a deal. So let's try one. So let's say we wanted to do the double integral upon R, a region of the square root of 2 dA. So we're just going to say z has a constant height of the square root of 2. All right? And so let's define the region. And so the region would be xy values such that 2 is going to be less than or equal to x, which is going to be less than or equal to 6. And negative 1 is going to be less than or equal to y, which is going to be less than or equal to 5. Okay? Now, like I said, the order of this doesn't matter. So I'm just going to pick one. And so I'm going to say, well, I'm going to do y second. So negative 1 to 5, and the integral from 2 to 6 of the square root of 2, now dx dy. Okay? So the 2 and the 6 are corresponding to the integral with respect to x, and the negative 1 and 5 are going to be corresponding to the integral with respect to y. Right? So the first thing to do is just, this is a constant right here, so let's integrate it with respect to x. And so if we integrate with respect to x, so constant, it's going to be that constant times x. So that's going to be, all right, now the integral from negative 1 to 5, now the square root of 2 times x, evaluated at negative 1 and at 5, and it's still the integral with respect to y. Okay? So this is just like in calculus 1. So we're going to evaluate the integral at those 2 points. So let's leave our outer integral alone. That's the integral from negative 1 to 5. Okay. Sorry, that's 2 and that's 6. Right when I'm thinking about doing my next step. Sorry. Okay. So we integrated with respect to x, we're going to plug in our boundaries times x. Okay? So that's going to be root 2 times 6, now minus root 2 times 2. This is going to be an integral with respect to y. Okay? So keep the boundaries right. And so, all right, so what is that going to be? So that would be just 6 minus 2. So that would be the integral from now -1 to 5 of, let's say, let's just call this root 2 times 4, an integral with respect to y. Yep. Sometimes I have a tendency to get ahead of myself. Okay, so now we're going to do this integral with respect to y. So this is going to equal, now the square root of 2 times 4. All right, we're integrating constant again, so we're just going to insert a y right there. And then we're going to evaluate that guy at -1 and at 5. So that's going to be the square root of 2 times 4 times 5 minus the square root of 2 times 4 and then multiply by -1. Okay, so we have, let's just pull that square root of 2 times 4 out, and then we have 5 minus -1. Okay, so that's going to be 5 plus 1, which is 6, and so 6 times 4 is 24, so this is going to be the square root of 2, and then multiplied by 24. Okay. Okay, so let's try another one. Okay. So instead of a constant, let's actually have a function. And so let's say we had the double integral across R of x times secant squared of y dA, and let's let R, semicolon that goes to separate this, equal the x, y values such that 0 is going to be less than or equal to x, which is going to be less than or equal to 2. I've got to run out of room here, so just put a comma, and 0 is going to be less than or equal to y, which is going to be less than or equal to pi divided by 4. Okay. So once again, we have a rectangle that we're wanting to do a double integral for, but this time we actually have a function. All right. And once again, the order of this integration doesn't matter. See how I did it? I decided to integrate with respect to y first. So, say this is going to be the integral from 0 to 2, and the integral from 0 to pi divided by 4 of x, now secant squared of y, and this is going to be dy dx. Okay. Now, when you're doing double integrals, whenever you're doing the integral with respect to y, just ignore the x's, treat them as constants. If you're doing an integration with respect to y, so the only thing that you're paying attention to is the y. So right now, what we have to think about is, well, what is the integral of secant squared of y? Okay, well, what is the derivative of tangent? The derivative of tangent is secant squared. So that means that the integral of secant squared is going to be tangent of y. Okay? So this is going to become, right, so we're going to leave our integral with respect to x alone. Okay, so we'll leave that 0, not 2, just sitting right there. And this is going to become now x tangent of y. Now evaluated at 0 and at pi over 4, okay, dx. So we're just doing the inner integral at this point. Okay, so now let's evaluate that integral at those 2 points. So this would be the integral from 0 to 2, now of x, and I'm going to write this like this. Let's say tangent of pi over 4 minus tangent of 0 dx. Okay? Now, tangent of 0 is just 0. Okay? Tangent of pi over 4, yeah, coming back from trigonometry, well, tangent of that's 45 degrees, 45, 90. So tangent of pi over 4 is just going to be 1. So what we're going to get from this is that this is just 1 minus 0. Okay? So then this becomes the integral from 0 to 2 of x dx. Okay, so now we got just a basic integral to deal with. So this is x squared divided by 2, evaluated at 0 and at 2. And so, well, that's 2 squared divided by 2 minus 0 squared divided by 2. So redundant to write the 0 squared divided by 2. But what do we end up with this? We end up with 2 squared, which is 4. 4 divided by 2 is 2. And so our answer for that problem is just 2. Okay? Okay, let's try one that's a little bit more complicated. Instead of writing down the region, I'll just go ahead and write down what the integral is. So, let's say we wanted to do something a little bit more complicated. And so we're going to say, what about the integral from 1 to 4 of the integral from 1 to 2 of x divided by y plus y divided by x, and let's go dy dx. Okay. So then we have to consider, all right, now we have to integrate 1 divided by y and y. All right? So, what will this come out to be? So, that would become the integral from 1 to 4. All right, now 1 divided by y would be x times the natural log of y. Okay? And it's going to be easier to write this one just like this, plus y squared divided by 2 times 1 divided by x. Now evaluated at 1 and 2. And we still have our dx, because we haven't integrated the x values yet. Okay. So we integrated with respect to y, so those are my y boundaries, and so we're going to plug those y's into this thing right here, into both of them. So this would become the integral from 1 to 4 of x times the natural log of 2 minus x times the natural log of 1, and then plus, that would be 2 squared divided by 2 times 1 divided by x, and then minus 1 squared divided by 2 multiplied by 1 divided by x. And we still need to integrate with respect to x because we haven't done that yet. Okay. So, first off, the natural log of 1 is 0. So we can go ahead and throw that term away. And then if we think about these two terms over here, we can go ahead and make a combination of these. So 2 squared divided by 2 is going to be 4. 4 divided by 2, which is 2. And then, well, 1 squared divided by 2 is 1/2. So we have 2 minus 1/2. So 2 minus 1/2 is really 3 over 2. So this is going to become the integral from 1 to 4 of x times the natural log of 2, and then plus 3 divided by 2 times 1 divided by x, and we still have to integrate with respect to x. Okay. So let's go ahead and integrate with respect to x. This is going to become, well, x squared divided by 2 multiplied by the natural log of 2, and then plus 3 divided by 2 times the natural log of x. Now all of this evaluated at 1 and at 4. Okay. So now it's going to become, all right, so this is going to become 4 squared divided by 2 times times the natural log of 2 minus 1 squared divided by 2 times the natural log of 2. Now plus 3 divided by 2 times the natural log of 4 minus 3 divided by 2 times the natural log of 1. So we're just plugging our 4 and 1 into our x positions because that's the boundaries we're dealing with x. Okay? Well, it's not really a good way to combine all this. Natural log of 1 is 0, so we can throw that term away. This guy is really going to be 16 divided by, I'm going to read this as 16 divided by 2 because I'm going to subtract 1 divided by 2, so 16 divided by 2 minus 1 divided by 2 would be 15 divided by 2. And so the cleanest answer I'm going to actually get to this thing is 15 divided by 2 times the natural log of 2 and plus 3 divided by 2 times the natural log